out the vast, lonely approaches to the star called the named planet Ocean.
For nearly 3/4 of its surface is covered by water, and cannot begin to reach a full understanding of the world he inhabits without a greater understanding of the sea. In the beginning, the ocean was the cradle of life, and from its waters have come the creatures of the earth. From tiny mites that live and die on the borderline between land and sea, to monsters of the deep, the ocean is the ancestral home. Even those which migrated to the land show the ancient heritage in the fluid of their bodies, for chemically it is nearly the same as the waters of the sea. The ocean is sometimes a barrier, isolating animals of the land, but it is also an avenue, circulating and spreading life. Man himself found the ocean a barrier, but when he conquered his fear and ventured forth, it became a broad avenue for him as well. But it was not until late in the 19th century that men started to gain a more exact knowledge of the sea. In 1872, HMS Challenger, a 200-foot corvette of the British Royal Navy, began a 3.5-year cruise that was the first truly scientific investigation of the entire ocean. With this cruise, the shape and depth of the oceans were accurately described for the first time, and a fantastic amount of new information was obtained. There was such attention to detail that 4,417 new species of living things were discovered and named. In fact, the results of the Challenger's 70,000-mile voyage of exploration took 40 years to compile and filled 50 volumes. Here was one of the first major steps leading to the modern science of oceanography. Today, from many countries, there is a fleet of ships, large and small, following the trail blazed by the Challenger. Supported by modern craft and equipment, operating far below and above the surface of the sea, this fleet is the tool of a hardy breed of scientists. These men combine the sailor's love for the sea with the scientist's urge to search out the hidden relationships of nature. These relationships are so complex and interwoven that scientists from many fields are brought together in the common search for knowledge of the sea. Physicists are interested in temperature and density and movements in the sea. Biologists are attracted by the richness and variety of marine life. Meteorologists observe the close relationship between sea and atmosphere. Geologists search the ocean bottom for answers to questions. And chemists analyze seawater to learn more of its complex nature. It is part of the scientific method to proceed from observed facts into the unknown, a step at a time. And since the ocean is essentially a large mass of water, some knowledge of this substance, known as H2O, is basic to any study of the sea. Because it is so plentiful, water is often taken for granted as a common stuff. But actually, it is one of the most remarkable compounds found on Earth. Let's take a look at one small drop.
Pardon me. I'm just a little drop of water out of the restless sea. Right now, I'm seawater, and I'm pretty salty. Now, if we take out the salts, what's left is just plain H2O, but it's still me.
Of hydrogen and 1 atom of oxygen. What do you get? Terribly wet because it's H2O. H2O, water, 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 H2O.
Water is the only substance which exists as a liquid, a solid, or a gas, simultaneously and abundantly at temperatures and pressures normally found on the Earth's surface. And most important of all, nearly all of it remains a liquid. Remarkable, too, are water's thermal characteristics. It absorbs a great deal of heat energy while raising its own temperature only slightly. Also, water cools very slowly because it has a larger heat storage capacity than any other substance.
You know, even if we put the salts back in and make me seawater, I still do about the same things. And there are zillions of little drops, exactly like me.
Since the oceans contain over 98% of all the water on Earth, including that in the atmosphere, they have a far-reaching effect. The oceans temper the climate of many coastal areas around the world. They exert a profound influence even in regions far removed from the sea. But behind it all, the remarkable qualities of water are the principal factors in determining the character of the entire ocean.
It can be a rolling sea, or just a vapor puff, or frozen in a solid form. It's quite remarkable stuff. Go on, restlessly, night and day, endlessly. It never stops, it just keeps going, the restless sea.
You know, us water drops are a very fluid organization, and we really get moved around. Of course, it does usually take something big to get us started, like the sun or the moon. They cause tides, you know. Tides don't just happen. It takes pull.
The sun, the moon, and the earth are held together by the gravitational pull of each upon the others. This attraction by the sun and the moon causes tides in the ocean. But since the moon is nearer, its effect is greater. If the earth were a smooth globe covered by a very deep ocean, this would be easy to see. The moon would pull out a bulge of water toward it, and the earth would be pulled away from the water on the other side. There would be two simple high tides lined up with the pull of the moon. But of course, the earth isn't like this. The ocean is relatively thinner than the skin of an apple, and there are continents blocking most of the seas. It is only in the Antarctic, where the ocean goes all the way around the world, that the water effectively bulges out and stays lined up with the moon. The bulges shown here are, of course, greatly exaggerated. Now, as the Earth turns and the broad channels between continents come into line, long, low waves move northward at about 450 miles per hour. The crests and troughs are about 6 hours apart. And as they progress, these waves swing into complex patterns, making the high and low tides experienced on nearly all seacoasts. There can be several high tides in the ocean at the same time. But tides are also affected by the size and shape of the ocean basin. In any basin, water tends to rock back and forth with a natural rhythm which varies with the size and shape of the basin. If the basin is open to the sea at one end, the high point of the rocking motion can coincide with the arrival of high tides from the sea. This pushes the rocking water up higher and exaggerates its up and down movement at the other end. Nova Scotia's Bay of Fundy is an extreme example of this action. The rocking motion takes about 12 hours here, and in this time the water level changes as much as 60 feet in places. Ships that must remain anchored settle into cradles built for that purpose. Vast mud flats lie exposed. Then inevitably the water begins to rise again. Here, the movement of hours is compressed to minutes by time-lapse photography. In the mouths of rivers that open into the bay, a strong current develops, and sometimes even becomes a rushing wave front called a tidal bore. In the St. John River, there are rapids that flow toward the bay when the tide is low. But as the bay rises, water surges upstream. For a while, there is a violent conflict, until finally, the rapids are reversed. These tidal bores are found in a number of rivers around the world. The most dramatic rise of water is found when normal high tides are piled on top of water already raised by onshore winds and low air pressure associated with the storm. If the violent winds and giant waves of a hurricane are added, there are all the ingredients of a major disaster.
Ouch. Let's see. Where were we? Oh, yeah, waves. Waves are caused by another organization in the air. And when they get stirred up, they push us around. But it's really the sun that gets things started.
Energy from the sun, radiating through millions of miles of space, constantly bombards the Earth. It is absorbed by land and especially by the sea. Some of the energy goes into the surrounding atmosphere, causing the air to move. Acting upon each other, the ocean of air and the ocean of water can be considered a giant heat engine driven into motion by the sun. The ocean of air, moving across the surface of the water in the form of winds, drives in turn the most familiar of all movements in the sea, waves. Exactly how waves start is one of the unsolved questions of oceanography. But the surface of the sea is nearly always in motion. And it is known that if wind blows steadily over this surface, the slight mounds of water pile up, and friction with the wind could be dragged along in moving waves. As the wind increases and continues, and the waves grow in size and speed. The highest waves are born in the long, unobstructed reaches of the sea, where howling gales may blow for days on end. 30-foot crests are not uncommon here, and even monstrous 50-foot waves are reported. As the waves move out from the storm area, only the longer, more rounded forms remain. And these symmetrical swells can travel for thousands of miles. It is this kind of wave that is most excellent for surfing. But scientists as well as surfers are interested in waves. They study waves by direct observation, theoretical analysis, and practical experiments in wave tanks of different sizes and types. Idealized waves are created by mechanical means. It can be seen that while the wave is a form moving through the water, surprisingly enough, makes very little progress forward. Another interesting experiment shows that the water particles move in nearly circular orbits that become smaller with depth. As the waveform moves into shallow water, it slows and becomes steeper. And when there is not enough water for the particles to complete their circular movement, the wave collapses forward as a breaker on the beach. Although the waves roll in with endless variety, the curling motion of the water is clearly seen. Smashing breakers chisel rock, undermine the land, or carve patterns in the beach. When waves sweep in at a slight angle to the beach, they set up currents along the shore which transport millions of tons of sand each year. Any obstruction projecting out from the shore causes sand to be deposited on one side and carried away from the other. Another result is found in areas where longshore currents turn seaward in what are known as rip currents. These areas can usually be recognized by the turbid appearance of the water. A swimmer caught in such a rip can quickly become exhausted trying to swim against the current, but he can escape by following one important rule. Swim parallel to shore for a good distance. In doing this, he is soon out of the rip current and able to return safely to the beach.
Rip currents are tricky, all right. But speaking of currents, when us seawaters get pushed around by the air, we get stirred up into some really big ones. Whoops!
On a worldwide scale over land and sea, the wind systems are complex, moving in enormous circulating eddies. Here we see those which blow over the oceans. These winds drag the water into movements that also have generally circular patterns. Sailors have ridden these winds and currents for centuries, even without understanding their cause. In the Pacific, Spanish ships known as the Manila galleons followed them between Mexico and the Philippines for over 2 centuries without discovering the Hawaiian Islands. In the Atlantic, others found similar winds and currents, and soon learned that a southerly route made for an easier and more certain passage to the west. But as late as 1769, mail packets coming directly from England to America took 2 weeks longer than ships going the other way. Benjamin Franklin, as Deputy Postmaster General of the colonies, noticed this. Using information obtained from whaling captains, he was instrumental in publishing the first chart of the Gulf Stream. Today we are learning more about these great ocean currents and oceanographers spend many days at sea tracing the movements. Current meters are used to measure the speed of the flow, and radio buoys, which send out continuous signals, show patterns of movement over a long period of time. Many of these data are correlated with the aid of modern electronic equipment, and from all this information, scientists are building up a more accurate picture of how these currents work. Using the Atlantic Oceans as an example, we find that here, as in other parts of the world, the constant trade winds are the main drivers, forcing the water to flow in two broad westerly running rivers, the north and south equatorial currents. As these currents come up against the land masses, they are shunted to the south and north. And if we follow the northward flow, we find the famous Gulf Stream. This tremendous meandering river in the sea, twisting and mixing at the edges, sweeps along at 4 to 5 miles per hour and flows with a volume 75 times greater than all the world's rivers combined. Moving farther northward, the current slows and starts to spread, but it is urged on again by prevailing winds from the west. Turned aside once more by a land mass, some of the water moves southward, completing the circuit. South of the equator, there is a similar system, although rotating in the opposite direction. There are corresponding currents in all the major oceans, and they make a vast interconnected system by which surface water is exchanged around the Earth. There is still much to be learned about these currents. For example, scientists have discovered currents just below some of the surface flows, but running in nearly the opposite direction. This unexpected discovery is exciting to oceanographers and is also a reminder that the oceans are deep as well as broad.
Well, here we are back in the old Restless Sea. Now, you may think it's just the same from top to bottom, but it really isn't. A couple of my friends and I will demonstrate.
As seawater becomes colder, it becomes heavier and tends to sink. But when it is warmed, it becomes lighter and tends to rise. When water evaporates, it leaves its salts behind. This makes the remaining surface water saltier, which makes it sink again. And then, if it gets colder, it becomes the heaviest of all. Waters of different density tend to form layers and remain separated for a surprisingly long time. In the sea, different density is often caused by a marked difference in temperature. The zone of separation is usually called a thermocline. There may be several thermoclines in an ocean, but there is usually a single main one separating the surface layer from colder water below. Water in the top layer moves primarily in the form of wind-driven surface currents, as we have seen. That below also moves, but the movement is slow, caused largely by differences in density. The movements are complex, but the principle can be illustrated in a simplified diagram of the South Atlantic. Some water moves northward at the surface until it drops down under warmer water. Continuing across the equator as an intermediate layer, it diffuses in northern waters. Again to the south, close to the Antarctic continent, other cold water is sinking. It is the densest water in the sea and creeps northward along the ocean floor. Sandwiched in between is another layer of water which originates in the north. To illustrate the speed of the main deep flows, water which started in the north about 1300 AD when the Crusades were ending had covered 1/4 of its way when Columbus discovered America in 1492. At the halfway mark in the early 1600s, the Pilgrims were landing at Plymouth Rock. And it neared the south in the late 18th century, about the time of the French Revolution. This same water is just coming to the surface in the southern oceans today in a never-ending cycle. In such areas, there is a great abundance of sea life. This is made possible by the rich supply of nutrients the upwelling water has taken on during its slow travel at great depths.
Water from the ocean. Foaming waves at sea
And breakers on the shore aid in this process by churning up billions of tiny bubbles. This laboratory experiment shows in slow motion how bubbles bursting on the surface toss up tiny droplets, exposing more surface to the air and speeding evaporation. Winds carry the vapor aloft where it condenses into clouds and rain. The falling rains water the land, of course, but in addition to this, as they soak the earth, the water softens the soil and dissolves some of the minerals in it. Muddy streams and rivers find their way to the sea, and an essence of the land is mixed into the ocean.
The thing you have to remember is that us water drops dissolve just about anything. And you'd be surprised at what we are made of. Let's drop in on my analyst. He'll tell you.
Seawater is extremely complex chemically, but it is known that in any given amount, about 96.5% is plain H2O. The remaining 3.5% is made up of various dissolved salts and chemicals. Most of this solid material is composed of sodium and chlorine, which combine into ordinary table salt. The remaining part is made up of other elements. These are magnesium, sulfur, calcium, potassium, and another group in smaller proportions. These are bromine, carbon, strontium, boron, silicon, fluorine, and another group in even smaller proportions. These are nitrogen, lithium, rubidium, phosphorus, and iodine, plus still another part, very small, but very important. Scientists have not yet been able to measure accurately everything in this part, but they believe it holds a trace of every other element on Earth, plus vitamins and other organic compounds necessary to living things. Thus, seawater is truly an Earth soup, having in it the raw materials so essential for the miracle of life.
See what I mean? We got everything. Oops, now cut it out. Well, that brings up the subject of life in the sea. You know, it's a good thing you can see right through me, because that's what the sun does. And that's how this whole life business began.
The sun pouring light upon the Earth is the source of energy for the chain of life. Plants in the sea, like plants on the land, are the first link in this chain. But they alone can use the sun's energy to convert carbon dioxide, water, into their own substance by photosynthesis. There are certain contrasts between land and water plants, but along the shore, in the zone between high and low tides, there is a transition. Here, plants and animals must adapt to the in and out movement of water and alternating periods of submergence and exposure. The plants are low and tough and cling tenaciously to rocks on the bottom in order to survive. Some animals creep about or burrow in search of food. Others attach themselves to rocks and strain food from the water as it washes by. In water that is only slightly deeper, the character of life begins to change. Some plants still cling to the bottom. These have long stems extending to the top of the water and are giants of the marine plant world. Most animals here still comb the bottom for food. But in the water from this zone outward, most living things float or swim to live. Life is most abundant in the upper level. Here, light can penetrate, and wind stirs and mixes the water, retaining the fertilizing minerals, phosphates, nitrates, and silicates. Where this mixing does not exist, nutrients tend to sink. Such areas are characterized by the intense blue color of the water and are nearly barren of life. Where the wind blows constantly offshore, the surface water is dragged away from the coast, and deeper, nutrient-laden water comes up to replace it. Life is particularly abundant in these areas of upwellings, making a rich ground for the marine biologist to study. Microscopic plants and animals called plankton, or wanderers, make up the bulk of this life. Most abundant are the diatoms, tiny green plants encased in jewel-like shells with an incredible variety of shapes. There are perhaps 15,000 different species drifting at the mercy of winds and currents. The animal kingdom has its wanderers too, and they graze upon the tiny plants. Most never grow beyond microscopic single cells. But some grazers do grow larger, such as copepods. These tiny animals are an important step in the food chain of the sea, for they are consumed by small swimmers, like herring and sardines. Here begins the domain of the predators, animals that feed upon other animals for their life energy. There is a savage but impersonal struggle for existence everywhere in the sea, as animals of different species compete for survival. But there are paradoxes too. Some whales, the largest animal in the sea, feed directly upon plankton, the smallest. And there are many unusual relationships in the sea where animals of different kinds help each other. Cleaner shrimp, for example, get much of their food by meticulously cleaning the gills of certain larger fish. In all the oceans, this chain of life is a constantly repeating cycle, and only about 1/10 of the remains of the plants and animals drifts down into the deeps. This is a gentle rain that began ages ago with the appearance of life in the sea. Some of this organic debris is decomposed by bacteria as it falls, and the vital minerals are redissolved in the water. Much of the rest becomes food for the denizens of a world of radically different, absolutely barren of living green plants. Most animals native to this zone are small, for the food from above is generally small in amount and size. The swimmers are fewer in number and variety. These creatures are among the most bizarre fish in the sea, with luminous spots, or glowing organs, or ferocious-looking teeth. In all the oceans, the slow fall of tiny skeletons and flakes of once living matter continues century upon century, some of it reaching the bottom. Part becomes food for creatures of still another realm, for there is life on the very deepest bottoms. Temperatures are barely above freezing, and the creatures here, brittle stars, sea cucumbers, spindly sea spiders, and tiny crustaceans creep about or burrow blindly under tremendous pressure. Sometimes a cloud of mud and sand called a turbidity current disturbs the calm of the deeps. Having started as a distant underwater landslide, it finally settles and becomes part of the soft carpet of sediments on the ocean floor. In the layers of sediment on the ocean bottom is a record of the Earth through geologic ages. And man has found a way to bring a part of this record to light intact. This device neatly extracts a vertical section of the sediments, like taking the core from an apple. The bottom sample obtained from this piston corer, as it is called, represents perhaps 1 million years of sedimentary deposits. The separate bands tell of different events within this period of the Earth's history. This band, for example, may represent an entire ice age. In the laboratory, scientists can determine the exact nature of the event by studying the composition of the various layers. This sample, composed of tiny particles of volcanic ash, records a 10,000-year period of large-scale volcanic eruptions. Other sediments tell other parts of the story. For example, some are composed largely of the remains of single-celled animals. Some of these animals lived in shells made largely of calcium carbonate. Most abundant of these are ones called Globigerina, some species of which are peculiar in that their shells curl to the left in cold water and to the right in warmer. This gives a clue to the Earth's climate at the time the animals were living. Developments in oxygen isotope analysis permit an estimation of the temperature of the seas at various times in the distant past. To find the age of different sediments, scientists measure amounts of radioactive elements. Carbon-14, for example, permits them to date back 40,000 years in the past. Newer techniques are being developed in the analysis of other isotopes by which sediments several 100,000 years old can be dated. But oceanographers have other ways of obtaining information about the bottom. With electronic equipment, they bounce sound waves off the bottom and time the echo, continuously recording the topography of the ocean floor. Distinctive features of the ocean basins thus recorded often give scientists other clues to the history of the Earth. This record shows a sunken beach, indicating that several thousand years ago, this was the edge of the sea. If such a beach could be seen clearly, it might look like this, with rounded gravel and small sea cliffs. Here we see the record of a submarine canyon. These canyons can be as large and precipitous as many on land. And if translated into a picture, it might appear like this. In some parts of the ocean, the records show that there are sharp projections called seamounts rising abruptly upward. In the same vicinity, there can be others with flat tops, which are called table mounts. From these, scientists have dredged up reef corals and other evidence that they once were islands, which millions of years ago sank beneath the surface. On an exaggerated scale, the topography of a whole ocean can be compared to a huge soup plate. At the rim is an almost flat margin called the continental shelf. This falls away more steeply in what is known as the continental slope and continues down to the floor of the abyss, which has an average depth of about 2.5 miles. Most oceans have a rise in the center of the floor and in some cases a ridge down the middle. In certain areas there are trenches nearly 7 miles deep. These trenches occur near the edge of an ocean and are associated with active volcanoes and many earthquakes. The Pacific Ocean, in fact, appears to be circled by a ring of fire. Why this should be is currently an area of intense inquiry by geologists. New volcanoes still rising out of the sea give evidence of tremendous forces at work deep within the earth. In the constant search for data, scientists must look beneath the ocean bottom. Magnetometers show different intensities of magnetism in various parts of the ocean floor. And thermoprobes measure the amount of heat flowing through the sediments from the Earth's interior. In another technique, depth charges are rolled overboard at regular intervals. Instruments on another ship can time the arrival of sound from the explosions. The sound travels through various materials at different speeds, reaching the instrument ship at different times. When the sound waves are recorded on a graph, it is clear that there are several distinct layers beneath the sediment. From these data, new theories are proposed. For example, this layer is shown to be rough, which leads some scientists to believe that it may be the original surface of the Earth. If this turns out to be true, the sediments may date the beginning of life and even give the actual age of the oceans. Scientists are finding other exciting clues to the Earth's structure that show the crust under the oceans to be much thinner than that under the continents, while both are believed to be floating on a deeper, more plastic material called the mantle. Some geologists theorize that there are slow convection currents within the mantle. They move only about 2 inches per year, but through the ages, this would be enough to bring about a tremendous overturn of material. But scientists want actual samples, as well as additional data about the structure of the Earth. With a project in progress today called the Mohole, they are attempting to drill through the sediments and crust into the dense mantle beneath. A preliminary drilling operation has shown the feasibility of this plan. Multitudes of questions about the sea remain to be answered, and new methods of obtaining information are constantly being developed. Bathyscaphs such as the Trieste are used for exploration at great depths. Oceanographers have taken the Trieste on a dramatic dive of nearly 7 miles to the bottom of the Marianas Trench in the Pacific. This strange-looking craft, called Flip, was designed for studies just under the surface of the sea. When its tanks are flooded, the vessel slowly comes to an upright position. This gives oceanographers a stable instrument platform relatively free of the rolling, pitching movements of the surface. In shallow water, television cameras serve as a means of observation. Here we see oceanographers setting up a stationary camera on the ocean floor. A connecting cable carries the picture to land, where a monitor screen can be switched on at any time to view the comings and goings of life on the bottom. At the same time, a hydrophone and tape machine record the many sounds uttered by curious visitors. Underwater television cameras mounted on remotely controlled vehicles are also being used by industry to inspect telephone cables and pipelines. Here is the picture transmitted as the camera follows a telephone cable along the ocean floor, allowing the observer above to check its condition and surroundings. Thousands of miles of new telephone cables are being put down in the sea, bridging the space between continents. Cables can also be laid offshore along the coastlines of continents rather than installed on land. This is only one of the ways utilized by industry. Large-scale conversion of salt water to fresh water is being extensively studied and tested. Relatively small pilot plants are able to produce up to 1 million gallons of fresh water and separation. This important metal is extracted in pure form. Such methods are being further developed to mine other vital minerals in the ocean. Even today, about finish, this source will become increasingly important. Ocean farmers are sowing and harvesting crops of seaweed in shallow waters off Japan, adding a valuable food supplement to their diet. Aquaculture, as this is called, can be further developed and may prove to be of great value in the future. Modern equipment is being used by the fishing industry, greatly improving its capability. However, there is much that can yet be done scientifically to add more of this excellent food to the world's supply. These are problems of practical concern. But oceanographers also have questions of wider scope and significance. Where did the waters of the Earth come from? How long have they been here? Are the great ice caps growing again, locking up more of the Earth's water, lowering the level of the sea? Or will they melt and flood the land? Are the oceans getting warmer or cooler, saltier or less salty? How might these changes affect the creatures that live out their lives near the sea, on its moving surface, or in its depths? While most animals came from the sea, why have some returned? Does another clue to the beginning of life lie buried deep in some ancient layer of the sea floor? Will the study of the ocean throw new light on unanswered questions about the origin of our Earth, or even the universe? Scientists of today and tomorrow may find in the sea answers to these questions and many others. But to man, the ocean will always be an overwhelming presence. Restless, ever-changing, it will remain a challenge to his questing spirit, his urge to explore the unknown.
Roll on, restless sea, night and day, endlessly. It never stops, it just keeps rolling, the restless sea.
The Bell System is grateful to the many distinguished scientists who helped prepare this story of the sea. Our thanks to those who supplied and checked the scientific content, and to the individuals and organizations who provided special material. Our thanks to the Advisory Board, which reviews the scientific aspects of these programs. Its members represent the broad range of modern science: biology and genetics, medicine, bacteriology and botany, chemistry, geophysics, physics, electronics and acoustics, mathematics, engineering. To all these men, the Bell system is indebted for their support of this venture in public education through entertainment.